Okay, in this video, we are going to cover a numerical example of lossy transmission lines, and we'll sort of see how this works for real. So let me show you the problem, and then we'll kind of go through it. So we're going to take a look at the data sheet for a cable by a company called Belden. The part number is 1217B. You're welcome to look it up. It's a specialty cable, in particularly optimized for the audio range. It's used, for example, in high-end audio concerts. So let's say you're an engineer and you're in the process of preparing Piedmont Park for a big concert, and you're using this cabling, right? So you're asked to figure out if this cable will work. You're going to connect it to an amplifier that is 10 kilowatts, and you got to run that about 1,000 meters away to the speakers all the way in the opposite end of this large field that's about 1 kilometer away. You know it's the audio range, so you've got to make sure that this works up to about 20 kilohertz. So let's ask ourselves a few questions. First of all, what's the impedance of the cable? What's the velocity of propagation? Do we need transmission line theory here? And then what kind of power can we expect to reach the back speakers? I think that's the important part. If we lose all the power before it gets to the back speakers, obviously we better find another cable or come up with some other solution, maybe put a repeater in the way. So that's the kind of the idea here. So first, let's gather up the properties, and I'm going to now show the data sheet for this cable that you're welcome to download yourself. This is a picture of it. This particular cable actually has 4 different twisted pairs within it. So you can see 3 of them easily. The 4th one is kind of in the back. Within each of those twisted pairs are 2 wires that again are sort of twisted together, and there's also a 3rd one which is a shield, right, or almost like a ground in between them. So there's in this case, it's kind of like you have a coaxial cable, but then you have another conductor around the outside of that coaxial cable, so that the different coaxial cables don't talk to each other and don't interfere with each other. So there is 4 of these 2-pair conductors, or 4 transmission lines in the same cable. Right, so here, 4 pairs. The gauge of the wire is 22 gauge. It's made out of copper, and here's the diameter of the full cable itself. All right, this is some information about the material, but if we go to the second page, this is where we're going to sort of see the important information. All right, so here's the inductance. Notice the units is microhenries per meter, so that's the inductance per unit length. And here's the capacitance is 62.3 picofarads per meter, so this is the value of C. Down here, this nominal conductor DC resistance is what we're going to be looking for the value of R. Right, so if we string along 1 kilometer of this cable, then that total resistance along the conductor is going to be about 49.2 ohms. All right. Now, not shown here is G. And so very often in these cables, R is what dominates and G does not. And so G isn't even listed here because it's too small to matter. So G in this case, we're going to take to be 0. All right, and there's some other information in these later pages here. But so those are those values. Let's kind of write this down and actually work through the problem. All right, so first, let's just remind ourselves of the formula for the total propagation number gamma, which equals the square root of R plus J omega L times G plus J omega C. All right, and we have a value of L equals 0.6562 microhenries per meter. A micro means times 10 to the minus 6th. Now we have a value of C equals 62.339, and that's picofarads per meter. The pico in this case means times 10 to the minus 12. We have a value of R equals 49.215 milliohms per meter. It was actually 49 ohms per kilometer, so I just converted it into per meter so we can get our units right, and G equals 0. All right. From this, we can figure out what the impedance of the transmission line is. Z0 equals the square root of L over C, which is about 102.9 ohms. And the propagation velocity, we're going to assume that this is low loss, and we'll find out that that's the case. In which case, the propagation velocity is just 1 over the square root of LC, which is 1.575 times 10 to the 8th meters per second. All right, by the way, the speed of light C is about 3 times 10 to the 8th meters per second. All right, so this cable is going to propagate waves at a little more than half of the speed of light. And that's pretty typical for a cable, 1/2, 2/3, 3/4 of the speed of light. That's pretty common, right? It doesn't quite go the speed of light, but you're definitely in the ballpark. So take these numbers and plug it in, and we're gonna take omega to be 2 pi f, where f equals 20 kilohertz, right? So 20 times 10 to the 3rd hertz. Plug all these numbers into our formula for gamma, and gamma works out to be 2.3 times 10 to the minus 4 plus J times 8.36 times 10 to the minus 4. All right, that's the value of gamma that we get from that equation up top. All right, once we've got this, we're ready to run with it. All right, so let's place that up here. Now this first term right here, the real part of gamma is what we're calling alpha. That's the real part. And this is going to tell us how fast the wave is attenuating. The imaginary part, this is what we're calling beta, and this is the going to define the propagation. Whereas beta defines the attenuation. All right, so first let's figure out what happens to the voltage. All right, so what's going to happen to the voltage is the voltage phasor as a function of Z will be equal to the voltage phasor at Z equals 0 times e to the minus alpha Z times e to the minus j beta Z. And when we're talking about power, we don't really care so much about phase, right? The phase doesn't impact the power, right? But the amplitude does. So let's just take a look at this attenuating part right here, right? This is going to define the attenuation. And if Z equals 1,000 meters, then this e to the minus alpha Z is about e to the minus 0.46. Right, so the voltage is going to be multiplied by this value of e to the minus 0.46. But the power is going to be the product of the voltage times the current. And the current is also going to multiply by e to the minus alpha Z. And so the power ends up doubling this, this attenuation, right? So the power is going to go as e to the minus 2 times 0.46 is going to be the reduction in power. Right, that's going to be the power level as a function of Z. And that works out to be about 0.63, right, which equals e to the minus 2 times 0.46. All right, so let's take 0.63 and multiply that by the 10 kilowatts that we started. So 10 kilowatts will become about 6.3 kilowatts. So depending on your requirements, you might that might be good enough. It might not be, but that's a way you can quickly calculate how much power actually reaches the end. Definitely a noticeable amount of attenuation. You certainly would notice the difference between 6 kilowatts and 10 kilowatts, but it's not so severe that it kills the signal. And you'll notice, by the way, that alpha was pretty significantly less than beta, not by orders of magnitude, but by enough that we can consider this pretty low cost. Right? It's about a factor of 4 less. All right, so with that, we can sort of understand for realistic cables, how it might attenuate wave signals. Now, I mentioned earlier that this cable is sort of specialized for audio signals, and so this was all at 20 kilohertz. The higher you go or lower you go in frequency, it's going to change this, right? So this 6.3 kilowatts is unique to 20 kilohertz, right? As you go to 30, 40, 50, you'd have to redo these calculations, and you get a different value of gamma, particularly alpha and beta. Right, so that was a numerical example, hopefully to show you how this all works. In the next video, we're going to talk a little bit more about this dispersion and about the physical nature of these attenuation and losses.